Hello and welcome to C++ Weekly. I'm your host, Jason Turner. And in this episode, we need to talk about this graph. This episode of C++ Weekly is sponsored by me. Be sure to check out the video description for important links about upcoming events, sponsoring the channel with Patreon, buying copies of my best practices and puzzler books, and how to contact me if you are interested in on-site training or remote code reviews. Hello, future Jason here. After recording and editing this episode, I had some members of my meetup point out to me that I needed to clarify the difference for static at a global scope and static in a function scope. So everything that I've discussed in these last two episodes about static constexpr and constexpr, I am referring specifically to data at function scope. So if I happen to have this, then this thing, big data here, is actually going to be duplicated across every compilation unit. That's not what I want here. This constexpr is already implicitly a global. I probably actually want something like inline constexpr auto whatever in the header file if that's what I need to do, so that all of the compilation units then have their implementations merged and we don't get a bunch of duplication of data at link time. So at the global scope, this is what we want. At the function level scope, this is almost certainly what we actually want. So enjoy the rest of the episode. I hope this makes sense. But keep in mind, function level versus global scope are two different things here. And in this episode and in the previous episode, I was talking about function scoped constexpr data. On the same day that my episode on stop using constexpr, use this instead, a friend sent me this link to QuickBench. I've modified it slightly for the sake of our illustration here, but this was my friend's point. That the static data that I recommended that you use in that episode for constexpr specifically is a little bit slower than the dynamic initialization. So this is, as we all know from that episode, make sure you watched it, this is initializing a blob of data in the current stack. And this version is initializing a blob of data globally in static storage for the program. Now, I recommended that you do this because copying data onto the stack can sometimes be expensive, and more to the point that this is explicitly a stack variable. We are saying, please give me a local copy of this. It is up to the compiler to decide how and when to optimize it. Now, I also said that technically the compiler is not required to initialize this data at compile time, to compute the data at compile time, I should say. Now, that is technically true, although, with more research and talking to experts, it is fair to say that we can assume that this data was in fact calculated at compile time. It's possible in some rare cases on older compilers and such that it was not, but let's just say that we can assume that it was. So static doesn't really change that, but it does change the nature of where the data lives. And in this particular case, the static is slower than the dynamic. This is worth digging into. So let's take a quick jump over to Compiler Explorer and try to reason a little bit about the code that is actually generated here. Now, all of this is the benchmark code that QuickBench inserted here from Google Benchmark. What we want to look at is the two implementations of digit dynamic and digit static. So digit static does a direct lookup into the map of data. The map of data lives down here. And digit dynamic, as can be expected, is actually setting up some stack space right here in the function call scope. And honestly, I don't really know what it's doing. It's clearly done some sort of a decode table of some sort. It's not just a direct lookup and copy of that data. It's doing something. So it's moving this value into the current scope. And then it's doing I don't know, the mouse over doesn't tell us. And it's doing another thing that we don't have any information on, followed by the same thing again. And then, copies the contents of the source operand to the destination operand and extends the value to 16 or 32 bits. Oh, well, that's an easy one. It knows what memory location it needs to look up, which is relative to the current stack pointer, and somehow index into this value. And, well, it does magic, shall we say. Let's go ahead and look back at QuickBench, though, because I did think that this was an interesting test case. And to be sure, for this small 36 bytes of data, the static version is slower than the dynamic version. GCC can reason about the dynamic version more because now we're talking dynamic initialization, not dynamic heap allocation, just for the record. Two confusingly similarly named things. 36 bytes of data. That is, let's see, 8 bytes fits into a register. So that is 5 registers worth of data, effectively. Let's just, for the fun of it, start increasing the size of this. Now, keeping in mind that this is bytes of data. This is 72 bytes of data. It happens to be 72 objects because they're characters, but I think that the size is really the important thing that we want to reason about. Okay, so we increased it to 72 bytes. We doubled the size. And we're still looking at the static code being 1.2 times slower. If we flip back over here to Compile Explorer, increase that size to 72, and then we will scroll down, and we see that it is doing even more magic at compile time. And the static version stays the same as a direct index into that chunk of data. Okay, so once we reached 144 bytes of data, we now see static as being 2.1 times faster than dynamic. Now, let's just, for the fun of it, go ahead and increase this quite a bit larger to say, I don't know, 2048 bytes, and we'll see if these relative timings change. Now, by the time we have it up to 2048 bytes, the dynamic is 65 times slower than the static. Now, you might say that this is contrived, but I was actually talking about generating compile time lookup tables. And that is often what we do with constexpr. It is either a very small value or it is a very large value, at least in all the code that I have written. And you will at some point see an episode from me about my JSON to C++ compiler, and this is 100% relevant to that code. So let's go ahead and flip back over to Compile Explorer. And it really just comes down to the fact that it's having to copy a bunch of data onto this stack. It's the exact issue that I was talking about. Just for the fun of it, we'll try to narrow down the exact moment that these two things cross. Okay, it appears to be at about 136 bytes that the nature of these two things swap. So at 136 bytes, static is slower. At 144, dynamic is slower. So that's the threshold. It's hard to reason about what the compiler is doing differently in these two cases. So let's take a look at something else real quick. This is an optimized build. It's O2. What happens if we take it back to, say, O1? So we know at 136 bytes in an optimized build of O2, static is slower than dynamic. Okay, so as soon as we take it to O1, we have static being faster than dynamic by 1.6 times. Let's go ahead and bump the size up a little bit. Like I said, if this is a relatively large data structure that we want to index into. And now we can see that the static is about 5 times faster than the dynamic for an unoptimized build. And this is interesting because you have to have a pretty specific set of circumstances for the dynamic stack-based object here to actually be faster than the static one. And in a debug build, the static one is basically always faster. If we just go ahead and do a quick O0 build of this, we can see that, well, the compiler really doesn't do anything intelligent here. It knows what these values are at compile time, but it has to copy them directly into the stack, which shouldn't be surprising to us. But we've been looking at GCC this whole time. Let's go ahead and do a Clang build. We're going to leave optimizations off, and we're going to keep this large set of data. So we can see here with optimizations disabled that Clang is 30 times slower. Let's take it back to my friend's original comparison of 36 values. Okay, so the static is still faster in an unoptimized build in Clang, even at only 36 values. Let's go ahead and turn the optimizations on though, because this is an important difference. Okay, so in an optimized build, they are exactly the same. And we'll go ahead and pump this up again to a very large test size. And they're still identical. So let's go ahead and look at this in Compiler Explorer. Change the compiler to Clang. And we have optimizations disabled here. So we see an actual call to memcopy in this case, which GCC has optimized away. I think even in O0, GCC was not doing a memcopy here. Let's go ahead and turn on optimizations though. And we can see that the dynamic and the static actually do the exact same thing in this case. And if I turn it up to a very large data set in Clang, they are doing the exact same thing again. The compiler has actually merged those two things both into static data. That's pretty interesting, I think. So if I were to remove the static version, the one that explicitly creates the static data, the compiler still creates a static blob of data for us. So this is a choice that Clang has made. It generates the exact same code once we turn on optimization, regardless of whether it is a constexpr static or not a constexpr static, but only in the case of optimization. So what have we learned? With optimizations enabled, Clang does the same code, no matter the size. And GCC is faster with data sizes that are less than 144 bytes, approximately. Clang is always faster with the static, and GCC is always faster with the static. So I still feel pretty good about that episode, saying that your default for constexpr data should still be static. In some esoteric cases, GCC might be a little bit faster. Otherwise, you're better in every other situation to prefer static constexpr over non-static constexpr, and I feel like it's still more in line semantically with what you actually want from this code. You, of course, feel free to disagree with me, but I feel like this has been a pretty good look at things, but we never looked at Visual Studio, and I cannot run a Visual Studio benchmark here, but I can pull it up in Compile Explorer, and I think we have a pretty good idea what to look for now. Okay, so by default, Visual Studio is doing some level of optimization. Let's turn on O2, which I believe is the recommended one. And we can see that it creates, well, a data table of 1024 bytes, which I guess shouldn't be surprising, really. And the dynamic code looks like, well, okay, the static code does the same indexing that GCC did in the static version, and the dynamic code appears to do a copy in, but then also do some sort of, no, I see, that's a jump. So it's doing an unrolled copy of the data, I believe, instead of calling memcopy. That makes some sense. All right, let's go ahead and make this a little bit smaller. Yeah, and it looks like we're getting that copy of data in locally again with no dispatch out to the static thing. So my guess is that we have the same scenario in Visual Studio as we did in GCC, up to the point that the size of data that's being copied in can be fully unrolled and copied and indexed straight away. Then Visual Studio is probably going to be a little bit faster with the local data on a relatively small data set with optimizations enabled. With optimizations disabled, I can say with a fairly high degree of confidence that we are going to be back in this scenario where the static indexing, which is what we have here, is going to be the faster option. So I think we're good. I think the things that we covered in the previous episode still stand across all three compilers. But if you find yourself actually saying, what happens if I change that from static to stack allocation, basically, then do it. Change it. Measure the code. See what happens. Still think static constexpr is a pretty good default in this case. So thanks for watching this episode of C++ Weekly, and be sure to subscribe.